Here, I want to introduce our presenter, Doug Kitch. Doug is a veteran webinar giver for us, does a wonderful job. Doug is a graduate of the University of Northern Iowa. Doug has been with us for 8 to 9 years now. Started out working in our test center, moved on into our global biomass group, working on wood and other grinding, and has now spent many years since, 6 to 7 years, working across many applications, but early on in particular, Inbiana specialized in roller mill grinding of agricultural products, corn, etc., but also works through all of our applications. Gained a lot of expertise. His official title, Assistant Applications Manager, overseeing all markets for us. Doug is a very experienced presenter. Doug has presented numerous times with Texas A&M at various short courses, aquaculture, pet food, animal aquaculture, things like that. He is a multiple time presenter at the U.S. Poultry Feed Mill Manager Seminar, also the Auburn University Feed Milling Workshop. Has been a instructor there several times. Recently completed, North Dakota State University's Northern Crops Institute course as a presenter there. So without further ado, I turn this over to Doug.
Thanks, Ryan. I know it's minor semantics, and I'm going to point it out just because you missed the threshold, but it actually has been 10 years, 10 whole years, so not 7 and 9. But anyway, don't need to focus on that. We'll get started here. As Ryan said, feel free to submit questions as we go, and we'll certainly circle back around to them once we get to the end. So we'll hop right in. We don't need to hang on this one too long. Hopefully you guys all are here for the fundamentals of roller mill grinding. If you somehow got this link by mistake, you're still welcome to join us and try to learn a little bit. So real quick on safety, just always want to touch on this. Guys, just please make sure whenever you're servicing your equipment, you're opening up, please make sure you're properly locking out and tagging out. So on this slide, I just kind of want to go through real quick. This is more or less so you guys all understand the different industries that are on the call today. So I apologize if I'm a little vague at times, but it's because there are so many different industries that are on the call today. So I can't get into too many specifics. So I'd be happy to get those specifics with you one-on-one afterwards. So again, I just do apologize because as you can see, there's anywhere from literally rocks to corn that we're grinding today. So just something to keep in mind as we're going, that most of the concepts will pertain to your application, but in the event that something doesn't seem quite right, it is possible that it could be more directed towards a different market. So let's just start off real quick by asking the question, why are we using a roller mill or a roll crusher? And typically for most of you, it's because that roll crusher is going to use less energy than what a hammer mill or maybe other various forms of grinders would use. And also, usually we get a more homogeneous grind from the roller mill as well. So if you kind of look at this chart I have over on the right side, that shows approximately a 710 micron grind coming from both a hammer mill and a roller mill. That blue line indicates the particle distribution for the roller mill, whereas the red line is from the hammer mill. You can see they're both averaging right at 710 microns, but that blue line is a much more homogeneous grind than the hammer mill. So that's a big reason. Depending on the products you're running, so this is a little more focused on the grain side, but usually we see less heating. We're not adding as much heat just because we don't have as much friction working as compared to a hammer mill or a pulverizer or something like that. And also, again, very application dependent, but because we aren't heating as much, we're also not going to lose as much moisture. So for those of you on the call that are more in the feed industry, that's less shrink that you're looking at there. A couple other ergonomic things is, they're not as loud. They usually 80 to 85 decibels is normally where these machines are running. Again, that can change a little bit. They don't produce the dust that we see from other forms of grinders. Again, that kind of shows in that particle distribution you can see on the screen. And because those rolls in the machines are not spinning as fast as other various grinders, we also have a lower risk of a thermal event or a fire in there. So then we've decided that the roller mill is the best option. Now we look at how does a roller mill work? Well, material is fed through a series of rolls, typically 1 to 3 pairs of rolls, in order to try to reduce the size. And that's how roller mills work. I appreciate everyone stopping out today. I'm sorry, that was a poor joke. I apologize. So let's start at the top of the machine and with your feeder and what its function is and the different forms of feeders. This is our pocket feeder. Many of you have this particular feeder, and what this feeder is doing is it's volumetric. So we are able to calculate the amount of volume that we have going through that feeder. You can see the pockets are right here is what it is. This is actually showing our high volume feeder. And then it's going to dump across the face of this magnet, which is shown right here, and down into the rolls. This particular feeder is very nice because it is volumetric. You are able to calculate how much material is going through your machine. And also it can be utilized where you can tie it right into the main motor amps, and you can speed up or slow down that feeder as needed, depending on what your motor load is. And it is also a positive shut off, I apologize. Because if you need to turn it off, you can simply turn off the motor and you will not be feeding any product into your machine. So we'll move on next to, oops, too far, into our roll feeder. Now the roll feeder is it's similar to the pocket feeder in that there's a spinning rotor inside the feeder housing. But what this is a very coarsely corrugated roll that you can see right here or along this whole length here. It runs the full length of the machine. And what this does is it utilizes a feed gate that opens and closes to allow more or less product through. So this roll feeder typically stays at a constant speed. This is a very nice feeder in the fact that it does create a very nice curtain of material that goes down through your rolls. So we see very little surging from a machine or from a feeder like this. Whereas with a pocket feeder, it's possible that you'll see some surging. You'll see your amps bounce up and down, and I'll touch a little later on why that could cause a little bit of issues. So the roll feeder is very nice in that regard. However, it does require this feed gate, which does have to adjust open or close depending on what rate you want to be running. It's standard. It's going to come with this hand wheel you can see down here. That's going to pivot this arm, which will open or close this feed gate away from the roll to open or increase or reduce the amount of material that is going through the machine. Now, if you don't want that manual input, there is an option to add a linear actuator onto that. And this particular option actually is utilizes a 4 to 20 milliamp signal, which you can again tie right into your controls and automation, so you can read your main motor amps to open or close depending on what kind of amp load you're trying to run on your machine. So that way there's a little less human input. You don't have to constantly be adjusting it instead of picking one set point. Now this feeder comes standard with some of our smaller type machines. It's just a simple hopper agitator. The picture on the left, I apologize, it's a little hard to see, but you can see this flange bearing here and this shaft running across. And what it is just a hopper agitator, which is this right here. It's designed to just keep product moving and prevent it from kind of bridging up. This works very well with free-flowing grains. So for those of you on the call that are grinding corn, this type of feeder is very adequate. And I'm sure many of you out there are even operating this particular type of feeder. It again utilizes a feed gate open or closed to regulate the amount of material coming through. It's a nice lower capital cost feeder if you want. If you don't have any need to control exactly the amount of material going through there or don't need to calculate your throughput, it works very well. Sorry, I have to remove the laser every time I want to change slides. Now let's talk about magnets, because hopefully every one of your machines that you're running does have a magnet still installed up within the feeder housing. Just going to play this video. Hopefully you guys all know how these work and you're cleaning them, but that you can see that they're swinging away from your whatever type of feeder you have in there. I'll play pretty quick. I'll play it again. I'm going to pause it. So you can see it swings out. Oh, I didn't even get to pause it in time. I apologize. So when that feeder swings out, just make sure you guys are cleaning it off frequently. I know sometimes they're overlooked, you forget to do them, but cleaning these off, making sure you're not getting any tramp material into your rolls and potentially ruining your rolls. So now that we've kind of quickly gone through the feeder, now we're just going to go down the line and see where our material goes next, which is into the roll. So let's start talking about some of the roll characteristics. And first and foremost, we need to start off by trying to decide how many rolls do we need to use for your application. As I mentioned earlier, usually it's 1, 2, or even 3 pairs of rolls. And why we need to decide that is, there's a little bit of overlap. There's times where a single pair will do it, or maybe the double pair. Either one will work, but what's best for your application. We have to take into account, obviously, capital cost. There's always that part of the investment we need to talk about. But, it's also what's your best operating cost. And, I'm going to bring up the fact that, if you're looking between a 2-roll crusher and a 4-roll crusher, single and double pair, if both will do the job, when we look at the 4-roll as compared to the 2-roll, we're getting additional roll surface area. So we're spreading the work out over more pairs of rolls. So sometimes it's a little easier to get the grind we're looking for, and we can get a more homogeneous grind when we have a little more control over it. If we look at, how many pairs is too many, a lot of your machines out there, we can actually add another set of rolls to them. So if you have a single pair, we can make it a double pair. If it's a double pair, we can turn it into a triple pair, and a lot of times get you a little more efficiency, some better roll life. But, as far as is there a limit, we tend to think the 3 pair is the max you should be running, just because as that material is going through your roll crusher, it is getting finer and finer after every single set of rolls it goes through. So if we look at this this tooling that we have over on the left side of your screen, you'll see some of the corrugations will cut into rolls. So on the top, I'm trying to show what like a triple pair would look like. You can see these coarser corrugations, and they're getting finer as we go because the material is getting finer. We have to have finer corrugations, otherwise you'll get big particles that'll sit in those little valleys, and really this almost acts like a little bit of a pocket feeder. So we have to keep getting those corrugations finer and finer as we go down. So if we start to get into the quadruple pair or an 8-roll machine, you can see we have these corrugations would have to be so fine, moving the same volume of material through a very tight roll gap with very shallow corrugations. You can't move the same amount of volume that you can through these coarser corrugations. So, there's certainly some applications where we can look at adding a 4th set of rolls, but you start to get into the challenge of how long are the corrugations going to last, and that bottom pair becomes quite the bottleneck as compared to your top set of rolls. There we go. So now let's quickly talk on how all those rolls are driven. And the examples I'm showing here on the far left, you can see we have one of our triple pair roller mills, and you can see 3 main drive motors. Each of those motors is driving the front roll on each machine, or what we call the fast roll. And then over here on the right side is our inner roll drive, or the IRD, as you may have heard. And actually, let's just go to the example on the bottom. You can see our main motor back here. We have main drive belts going to this front roll, or the fast roll. And then over here on the right side of the machine is our IRD side, which is shown up here in the upper right. So the back roll is driven off the front roll via belts and different size shivs. And we'll talk in just a second on what these different size shivs are doing and what they're used for. So the reason that we like to use one motor per bank of rolls, or sometimes there's 2, but we only drive them off the front rolls, is because we want to make sure we understand how much work we're doing on each set of rolls, because that's really crucial to how your material is going to grind, how uniform of a grind you're getting, and also how much wear you're getting on your rolls as well. So on a machine that has 1 motor per bank of rolls, it's really simple to balance your motor loads, because you can record the amps on every single motor and hopefully be able to compare the numbers and see how close they are to each other. If you do have a machine that does only have one main drive motor for 2 sets of rolls, it's still possible because we are only driving the main rolls, or I'm sorry, the front or fast rolls. So we can do just a little bit of math, and we can be able to calculate how much work we are doing in each set of roll. I kind of have the instructions over there on the right of how you would do that. And the reason for that is, like I said, it's product uniformity. We don't want to overgrind on one set of rolls as compared to the other. When you overgrind on one pair, you tend to create a lot of fines, more fines than if we were to spread the load out over a couple sets of rolls. And also, when you're overgrinding on one pair, you're going to wear those corrugations a lot faster than the other set of corrugations. And ideally, we'd like to wear those at the same rate. So it's just for the longevity of your machine. It's a lot better if you can really maintain and balance out the work over all the sets of rolls that you have. I mean, similar to the vehicles you drive, you have 4 tires on them. You want to wear those at the same speed, so you should be driving on all 4 tires. So to talk about the differential, mentioned it just slides back, and I've seen actually a question has already come in about this. All of those rolls, I shouldn't say all, but typically we're going to use a differential on our rolls. And what that does is it changes the speeds of the front and the back roll so that they're not spinning at the same speed. And what that does is it actually creates a little bit of a shearing action in there. So you're more, think of it as you're cutting the material instead of just smashing it together or compressing it. And that brings us a few benefits. Typically, it gives us a lot more control over the material we're grinding. We usually see less fines when we use a differential in there, and we're able to just get a little more uniform of a grind, typically because we're not creating as many fines. So on the right side, I have a little bit of a chart that kind of explains some of the different differentials we use, and kind of an example. If our front roll is spinning at 1,000 RPM, it does show on the right side of what the slow roll would be spinning at. You see that 1.67 to 1 and 2 to 1 down at the bottom. A lot of times that's going to be more in some of our soybean dehulling applications, where if you're hot dehulling, because the temperature, you need that extra shearing action. A lot of you, if you're in the grinding grain relatively fine, we'll use that 1.3 to 1.5 to 1 differential. That gives us a nice shearing action. And not a whole lot of 1-to-1s out there. I'm guessing some of you, if you're utilizing our 650 series, you might have that. But typically, we use at least 1.1 to 1, just so we can get a little bit of a shearing action in there. Now, we just talked about how the rolls are working and the material going through them. These devices, everyone has them on your machines, and I want to make sure we're utilizing them, because without them, we have the potential to have material actually going around the rolls. So we want to make sure all the material goes through the rolls. So up top, you can see there's a UHMW cheek plate. Get my laser pointer here. It's this piece right here. It's UHMW, and you can see it slotted right here, so it is adjustable, because as your rolls wear, you will lose diameter, and we want to make sure this contours to the roll. So what this piece is doing is preventing material from going around the ends of the roll. And now right here, you'll see is another plate. You can see it on each side. This plate is also adjustable. There's the bolt. There's one bolt here. There's one other one you can barely see here, but you can loosen those bolts, and this plate will actually slide up and down. And what this does as well is prevents material from bouncing over the rolls, because again, we want all the material we're grinding to go through the rolls instead of over. So making sure these are set, I see it quite frequently when I'm out in the field. These were lifted up when you change the rolls, and they never drop back into place. So what happens is you get a lot of material that's going over the rolls. So we want to prevent that. One of the easiest ways I do it is really, if you can just use like a flathead screwdriver and put it between the rolls and that plate and drop it down. Just the higher up you are on your machine, it's not as crucial, but certainly as you get down and you're getting finer, you want to have a tighter and tighter clearance on that plate seal. Now let's talk a little bit about the roll diameters and what the options are and some of the advantages. And for the most part, what I'm going to kind of hit on here is larger diameter is better. There's more advantages the larger you go. So I'm going to talk about these 3 main bullet points here. I'll bring them up each time, but On the left is a list of the different diameters of rolls that we have available in particular machines. A couple of these we don't actually offer new anymore, but there's a good chance there's still many of you running them in the field today. So the first one is the nip angle, and that is basically what is grabbing that material and pulling it down through the rolls. Yes, the corrugations are grabbing a little bit, but it's also the angle at which that roll is able to contact the material. And the larger the roll is, the more optimal that nip angle is. I kind of use the example shown down there at the bottom of there's a Ram truck and a golf cart. If you have to use one or the other to jump over a curb, that truck's going to be able to do it better because it has a larger diameter wheel as compared to that golf cart. Just because I'm sure a couple of you were joking about me using a Ram. I did have a coworker suggest that I use an F-150 here, but I told them I could not. I did not have enough room where that golf cart is sitting, so I couldn't use that as an example. So now to talk a little bit about increased surface area. So when you go to a larger diameter, you have more surface area on that roll as well. And what that's going to do is going to give you longer roll life. The corrugations are still wearing at the same rate, but because you have more corrugations, they're going to last longer in between the times you need to corrugate. So I give 3 examples here, just showing 3 different 36-inch wide rolls. So we have a 9-inch, a 12-inch, and a 16-inch diameter roll. That 9x36 has just over 1,000 square inches of roll area. That 12x36 has about 1,357 square inches. And the 16x36 has just over 1,800 square inches. So each of those is about a 33% increase as you go up. So you have the same width of machine, and theoretically, you can move the same amount of volume through that, ignoring the efficiencies with the larger roll diameters. But if you have 33% more roll area, we would expect you to get 33% more life out of those rolls before you need to recorrugate them. So that leads directly into what's your downtime. If you could remove one less corrugation and times you have to turn off that machine and shut your production down, what's that worth to you? So just something to keep in mind when you're looking at machines, and is there a potential there for some savings? And I guess I will add, when we move showing this list again, is that some of your machines can be retrofitted. We can convert a 12-inch machine to 13 3/4-inch diameter. And those of you that are running a 14-inch, we can also increase that to a 16-inch roll utilizing the same frame. There's just a few components we need to change on your shivs and belts, but so there could be a possibility we can increase the diameter of your rolls without changing anything else on your machine. Like I said, you get the benefits of, we would expect slightly higher throughput or increased efficiency, however you want to look at it, but somewhere in the 10 to 15% range, we could expect to see that kind of improvement. And then also you do get that added roll life as well, so there's value there as well. Now this one is a really important one that's many times overlooked or not thought of, and that's actually the roll deflection. Now this is a direct result of the roll diameter as well as the width of the roll. Both of these come into play. So that's why I did list the different widths we have for each roll diameter, as you can see. And as you've noticed, as the diameter gets bigger, we are able to get the roll longer. And I'll explain real quickly here why that is. Excuse me. So where that roll is the least supported would be in the very middle of the roll, where it's farthest away from the bearing that is affixed to the frame of the machine. So it'd be very difficult to see. Actually, I don't think you could see it at all, but that roll does flex a little bit, just because as that material is coming down into the rolls, my laser again here. So your material is coming down, and as it hits those rolls, it's actually trying to push those rolls apart. Now over on the edge of the machine where the bearings are and it's attached to the frame, they're really not going to move very much. But when you get into the middle of that roll, you could actually see that roll try to flex a little bit. Now, I talked earlier about that pocket feeder and you get some surging. Well, that can cause some problems, because if you're surging, it's trying to push it at times, and then it's not pushing the roll, but it's pushing it and not pushing it. So your roll's constantly moving. So that can cause some minor issues. But if we just look at the deflection, even assuming we have a curtain of material, that roller is going to try to push back a little bit. So if we look at a couple examples I did just to kind of show some of the more extremes, if we have a 12-inch diameter roll that's 72 inches wide, the middle of that roll can move up to 10,000ths of an inch. Now, if we narrow that down to just a 12 by 52, so I can show you how the widths vary here, that deflection drops to right at 400,000ths of an inch. And then if you, using that same example, if we increase our diameter from 12 inches to 16 inches, that deflection drops even lower, down to just over 1,000th of an inch. Now, again, we're talking thousandths of an inch here. Does that really make a huge deal? And actually, before I go on, sorry, the very bottom note I talk about is, some of you I can see, or I can't see, but you're probably thinking, hey, we have 72-inch and 84-inch rolls out there. Why would we do that if you're seeing that much deflection? Typically, those are the machines we're going to use in a very coarse grinding or a cracking application where we don't need to have a very homogeneous grind. And I'll show why here. I'll give you an example on the next slide. So I apologize, there's a lot of data on this. I will explain it. So what you're seeing are two particle size distribution reports. These are two different grinds that were run on a machine that had 12-inch diameter rolls that were 12 inches wide. So essentially minimal to no roll deflection at all. And what I did is I ran a sample and I kind of recorded the roll gaps up here. And you can see we got a mean particle diameter of 441 microns with a 1.89 standard deviation. And then to try to simulate that roll deflection you would see of 10,000ths of an inch, I opened every single roll gap up by 10,000ths of an inch. And what we got is a mean particle diameter of 593 microns. So we saw a 152 micron difference in that 10,000ths of an inch. Now, if you go back and you think, that's 152 micron difference. If we have a roll there that's can flex that much, you could be making a different grind just even though your roll gap's the same. As that roll is flexing, you're going to see your grind change. So that's why we don't like to use a machine that's wider than 52 inches for a grinding application, just because when you're 52 or narrower, that number, that deflection really drops down, and we're able to keep a much more homogeneous grind for a longer term. So let's talk about now, we're obviously trying to keep a homogeneous grind, and we can see some roll deflection and what happens. So how is your machine keeping those rolls together? How are we maintaining that consistent grind? Well, it starts off first by the frame you guys all have. It's a very heavy duty frame. I list the different wall thicknesses you can see there. But what I want to point out is the frame of your machine is only supporting the weight of the rolls. It's not actually holding any separating forces from those rolls trying to push out. It is just supporting the weight of the rolls. So it's already a very heavy duty frame. So just a real quick trivia question, because we can. Any guesses on what the weight of a triple pair 1652 roller mill or roll crusher is? And that's not including the motors. You guys are all muted, so you can't answer anyway. Oh, I see someone already actually threw it out there. Yes, the answer is D, 31,500 pounds. A is actually the weight of the rolls alone, so there's about 14,000 pounds of just frame on that machine. Yes, good job, Will. So also on that machine, just to point out, the frame is the only piece on your machine that cannot be replaced by the time that would wear out. We just assume you just need a new machine at that point. There is a piece on the frame that is replaceable. I just want to point this out real quick. It's that bronze bearing slide. So as that slow roll is moving in and out, there's a sliding surface, which is that bronze wear strip. That is replaceable. So that's just what I want to show on this machine, or on this slide. But so the frame only is supporting the weight of the rolls. So we need to have another enclosure that is holding together the separating forces. As those rolls are trying to push out, we need something to contain that pressure as well. So what we have on our machines, or you guys have on your machines, are these tension members, this whole tension member housing. And so the way this particular area works is this machine is showing a 5-ton ball screw jack, which is what's going to move your rolls in and out. It's going to hold your rolls in. And you can see our bearings up on this tension member, and then we have this tension member over here that's holding this side. Now on these rolls, you can see we have a disc spring, and on the next slide I'll show you some examples of those. But that's what's going to hold those rolls in, or if you do get an uncrushable object, I won't say rocks because some of you on this call are grinding rocks, but bolts or something like that. If we need to pop those rolls open, that's what those springs will do. But what I wanted to show here was it is this tension member that's affixed to your frame is what's actually supporting the separating forces of when you're grinding. So we kind of have two different areas on that machine. So you have the frame, which is only holding the weight of your rolls, and then we have this tension member enclosure, which is what's actually holding your rolls together to keep them from trying to move apart on us. Come on, next slide. There we go. So the springs I just talked about, depending on the series of machine you're running, they're going to look a little different. You can see up here on the top left, this is our 650 series, much smaller series of machine. So we don't have a very, high intensity spring going on. But you can see as our machine sizes get bigger, our spring stacks do get more and more robust. You get up to the 1200 and 1600 series shown down here on the bottom. You can see there's a double stack of beveled disc springs is what we're using there. Just like I said, as an uncrushable object does come into your machine. Hopefully they're not, but that will allow those rolls to pop open and hopefully allow that product to get through. And so there are a few different options that we use when we're looking at these spring stacks. And it's depending on your application. Like I just said, there's people on here that are grinding rocks, and there's some people grinding very, very simple stuff, such as corn or other grains. So we'll put a preload on those springs. That's what's holding those rolls together. And then we also have different deflection forces and over travel we can look at. So we can move anywhere from 4/10 of an inch up to a little over an inch, depending on what your application is. Again, like I spoke earlier, I'm going to keep it a little vague here just because we do have such a wide array of people on the call today. But basically, what I'm getting at is there are different options depending what you're looking at, and if your grind does change, if you're starting to get a much finer grind, and we want to make sure we're keeping those rolls as tight as possible, we may look at an alternative spring stack to try to make sure we're keeping those rolls from moving as much as possible. And real quickly, just to touch on this bottom bullet point, I'm sure many of you on here are operating crumblers as well in your feed facilities. The spring stacks are different for those. They are not as they're more forgiving. I'll put it that way. So most of them do not fall within the ranges I have up here. So they are just a little different. Now we're going to move on now to the roll adjust. So we just talked about how we want to try to keep those rolls from moving. We want to keep them in the same place. Well, once we do get them to where we want them, we want to make sure we can move them in unison. So we do have the single point roll adjust. So you only have to move one hand wheel per bank of rolls, and that roll is going to stay together and move in unison on both sides. Because once we get parallel, we want to keep parallel, especially as you get to a wider and wider machine. Keeping that parallel can be very difficult. That example I gave earlier on our 12 by 12 machine. That's not very hard to keep parallel just because it is so narrow. But as you get to that 52, 72, 84, it can become more and more imperative to try to keep them and keep an eye on them. So we do have the single point roll adjust, but as you're checking it, you may notice that your rolls aren't in parallel. Well, luckily we do have a very simple way to correct that. If you're on our 1200 or 1600 series, there's this coupling on the back that is connecting those jacks together. Hopefully you guys are all familiar with it. All you have to do is slide this coupling over, and you can move either side independently to get the rolls into a parallel position. And you reconnect that coupling, and you can continue to move that roll as you were before. For those of you on here that are operating our 900, 650, as you're aware, it's not that simple. I apologize. I actually, for whatever reason, omitted those slides from here, but you can certainly still do it. You have those threaded rods on each side, but for the 1200 and 1600 series, this is how we maintain our parallel. Now, all of your machines do have roll stops, which is what we use to prevent you from running your rolls together. Unfortunately, when you have to have a very tight clearance, if we're down to 2 to 3 thousandths of an inch, there's also the possibility they can run the rolls together. We don't want you to do that just because that's going to wear your corrugations faster, and that's going to increase your operating costs, which we don't want to do. So these roll stops are designed that we can set them to prevent your rolls from running together. Again, I'm showing our 1200 and 1600 series here. The 900s and 650s are a little different. Certainly be happy to always work with you guys and walk you through how to set them. Each application we're going to set them a little differently. So if this is something you're not familiar with, please feel free to reach out, and we're happy to walk you through it. Just so, like I said, I don't want to wear your rolls any faster than we have to. So making sure these are set. It's a very easy thing to do, especially if we're on site with you guys. This slide is just more informative, just kind of talking about the various shaft diameters we use in our machines. Just because as you could expect, as the diameters get bigger of our rolls, we're also going to use larger shaft. Kind of goes back to what we talked about earlier with the deflection, just making sure we're as robust as possible. As you get up to that 1200 HX and the 1600, we want that 100 millimeter, get a little larger diameter bearing on there as well. But not too much to talk to at this standpoint. Now, all of your machines did come standard with an aspiration port on them. Many of you that have I'll say older, but only if you haven't purchased your machine within the last 5 years, your aspiration port's going to look like this. It's that round, I think it's 4-inch diameter connection point on the back of your machines. We don't require aspiration to maintain throughput through your machine, kind of like a hammer mill would, but we do like that just for housekeeping purposes, and even to help protect your bearings a little bit. I'll talk about that just in a couple slides. But the newer machines that you'll see out there actually do have a full width of air pickup point. And we did that to help keep the velocity a little lower, because with that round 4-inch diameter one, you sometimes, depending on how much aspiration you were pulling, you got a pretty high velocity at that pickup point. We'd pull a little more good product than we wanted to. So we want this full width pickup point. And sorry, I realized my laser's not on. Here we go. So, and we do have one for each bank of rolls. And to talk about that just a little bit, I know a lot of people out there certainly think, hey, if we just put a little bit of negative on the discharge of the machine, we'll collect a lot of the dust. And I'm actually going to use this picture on the left to show you why that's not always the greatest plan of attack. So you can see this full width pickup point, and that's located right here on the machine, right here, and right here. So there's one on each set of rolls. So if we're just pulling negative air off the bottom of the machine, you're only going to collect the dust that's down here on the bottom, because if you go up around, you have these tight roll seals there, the roll seal over here, and your cheek plates. So there's not a lot of area for you to be pulling air from, especially if on your bottom set of rolls where your roll gap might be 1,000th of an inch. And if you have product going through that, you're again not going to be able to pull much air. So you can be pulling a lot of aspiration here from the bottom, but you won't be able to collect any of the dust that you're actually producing up on the top of the machine. So if you do want to put a little negative air on it, I do strongly encourage that you put them on every bank of roll, just because that's where you're producing the dust. That's where we're going to try to collect the dust. And because we do have various roll seals in there, I'm not going to call them an airlock by any means, but we do want to try to collect the dust wherever we can and prevent it from getting out through unwanted crevices, which again, I will talk about here on the next slide when we get into talk of the bearings a little bit. So the places that those dust could get out through the machine would be where your roll shafts are exiting of the machine. So we do have roll seals that you can see here mounted to the shafts. And so that's just a neoprene seal. That's gonna hold tight against the frame of your machine to help prevent dust from getting out. And which is also, then we get into our split housing pillow block bearings we use. We now do make them with an LOR seal to get that O-ring in there. The goal is just to try to prevent as much dust from getting into those bearings. Those bearings are designed to last the life of your roll. So if you're not seeing that or having issues, that might be a place an easy way to potentially increase bearing life if you are having some issues would be to put a little bit of negative on that machine, just to try to prevent a little more dust from getting out into those bearings. So also with maintaining those bearings, a lot of our newer machines are being equipped with this lubrication delivery system, or LDS as we call it. That way it's just a single point lubrication point on your machine. Again, trying to reduce manual points where you have to be adding grease to your machine. So if we put it all in the same spot, that's just really what this is. Again, I'm not going to get into a lot of detail, but most of your machines should have something like this on them. Now to talk a little bit about corrugations. I've seen a couple questions have already come in talking about the different corrugations and what's required. The corrugations are very dependent on the application you're grinding and how fine you're wanting to grind. So we're always happy to review them. One thing I really discourage you from doing is, when you send your rolls in for recorrugation, we hear it a lot of just give me what we've done before, just because that's what we've always done. For most of you, I'm guessing your grind requirements have even changed over the years and decades. So reviewing and making sure we are using the right one. And just real quickly, a quick guide on some of the more popular corrugations we use. The Sawtooth, the B&W, and the RBV you can see here. B&W, I know many times is also known as Buehler Cut. I obviously can't write that on our slide, but I will acknowledge that, yes, that's what is referred to at times. But I won't read through the bullet points. The B&W is very similar to the Sawtooth, we see a little sharper edge to it that lasts a little bit longer, is the benefit from that. And then our RBV is the most common corrugation we use for the majority of our grain grindings. So similar to the last slide I just said, feel free to utilize our applications team. Just because the corrugation you're using has worked pretty well for you for however many years or decades you've been operating your machine, doesn't mean that there may not be a better mousetrap out there for what we can look at, or if your grinds change a little bit, you're trying to optimize something a little else, feel free to have the conversation with us. That's what we're here for. We do want to make sure we let you know the options we have available. And one example of that is actually the blue rolls we've been working on here for a handful of years now. A lot of times we have a lot of ideas that you may not have heard of, you may not know exist. So we're happy to help you out with letting you know what we know. And this is just one example. If it's something you feel like you may be interested or have benefit, again, feel free to reach out to us. Rather not make this much of a sales pitch, so I'm not going to dig too deep into it, but it is an option that is available for you guys. So just quickly review kind of a lot of the points we've went over, and then we'll open it up for questions. Just the different points we've talked about and where they're at on your machine. I do show one of our triple pair machines here, so many of you may not, if you only have a single or double, obviously you could reduce it. This won't show the 900 series or 650, but you can see our 3 main drive motors, one for each set of rolls. You can see your jacks on the back of the machine. There's one on each side, so you can see these 3. There are 3 more on the other side that we can't see from this angle. You can see our disc springs that we were talking about, so that jack's moving that whole shaft in and out as it's moving the bearing and roll, I should say. Obviously, you can see the bearings on all the ends of the shafts. We did talk earlier about roll parallel and maintaining that. Another one is actually the roll tram. We didn't talk about that one at all. So that's kind of how your rolls, if they get it like cocked a little bit like that. Underneath these bearings here is actually a tram bolt that we can use to lift up or lower that roll, so we can make sure they are in proper tram. As these machines are sent out, we do send a tram gauge with all of them. Many times they do get lost, understandably so. But that is a tool that is sent out with them. You can see this cheek plate in here. We talked about that, sealing the end of the roll. It's hard to see those plate seals we talked about. You guys all have the sample ports on your doors, and then the swing out magnets and the feed gate we talked about earlier. And then we'll just go to one more on the back side, and then we can open it up to some questions. There's the back side of the machine. So again, you can see all your main drive motors for each one. Here's the jack on the opposite side that we couldn't see. You can see that shaft that goes across from jack to jack that does connect those together. And there's that coupling component that you can couple or decouple if you do need to reset your parallel on your machine. The single point roll adjust on each machine, and each machine is independent, so you can move each roll independently. Main drive is obviously over here, and then here's that IRD or inter-roll drive side we talked about. For the most part, most of your machines are in this configuration, but they can be flipped if we do need to. And then again, those aspiration ports on each machine. You can see another one right in here. The bottom one's kind of hidden, but it is right there. So that's a real quick review on those points we talked about. Looks like we got a good amount of questions coming in already, so I believe we'll take a look at some, but I do have my contact information here on this next slide. So if you guys do have any more questions, always feel free to reach out and we can talk a little more in detail specific to your process and your application if you want. And I will add another thing. If you guys do have any ideas for future webinars that you would like to learn more about anything across the CPM business, feel free to comment or send us a message. We always want to make sure we're bringing you guys content that you see value in. So please let us know if there are any future webinars you would like to hear from. So at this point, let's look at some questions.
Sure, Doug. We'll present the questions that are a little more general in nature. There's a couple of very, very specific questions, good ones, that will reach out to individuals, to each individual that asks the question directly and have a further conversation. First question, what is the relationship between the size of particles and the number of roll flutes per centimeter? And for corn, what is the perfect corrugation of rolls and flutes, corrugations, as we say, up from top roll to bottom?
I'm going to have to provide a very vague answer here of it depends. That'd be something, it would be better to have a conversation offline, especially just because wanting to know how fine you're wanting to get that product. How homogeneous do you need? Is there a certain standard deviation we need to hit? So there's no one great answer to that. So I can't provide you with just based on what I know at this point with what the proper corrugations would be.
So in that same vein, Doug, what is the differential speed of rolls for good crushing?
Same vein, yeah, sorry. Most likely, we typically like to be about that 1.5 to 1 for good grain grinding is typically where we see. Again, obviously, there's always some exceptions to the rule, but usually with that 1.5 to 1 is where I kind of like to start.
Okay. Is there a better seal on the roll shafts to prevent the outflow of dust? The current one is a sponge.
Yes, we do have a couple other options other than what was shown. We have your name and information of who asked this question, so we can certainly reach out to you with some other options that we do have available.
We do like this, like the sponge as was stated, but they do need to be replaced consistently, and relatively low value item, but it does require consistent replacement.
Yeah,
when they're new, we do think it's a good solution.
Yeah, that's a good point Ryan just made. Like he just said, they're relatively low and in cost. So when you are changing your rolls out, it is just a good component to just assume you're going to change it every time. That they might still be in good condition, but for the investment they make and for the dust they hold back, it is good to just replace those every time you do pull your rolls out.
Can you use different roll speed differentials on each bank of rolls?
Yes. This is something we many times use, especially if we're looking at a triple pair machine. We'll sometimes use a less aggressive differential on the bottom pair of rolls. And what that does is it actually makes your slow roll faster. So because like I talked about, those bottom rolls, you have them, the rolls so tight, they are a tighter corrugation. So many times that's the bottleneck in your machine. So we sometimes will actually speed up that slow roll on the bottom pair to help move a little more product. So it's a little less aggressive. Also, sometimes, if you're someone who's running different commodities or different products, yes, we'll use different differentials on different pairs if we're trying to utilize one set over the other with a different product. But the quick answer to that is yes, we can do that. Because I guess because each set of rolls has its own independent drive and IRD setup.
Okay, next question. how large of material is able to go into a roller mill? I'm asking for bigger than corn kernel size, like larger pellets, alpha or wheat bran pellets, 10 millimeter by 16 to 20 millimeter in length. Can a roller mill handle those?
So kind of the rule of thumb we say is usually 1/2 inch or smaller is what you want to look at, or 1/2 inch, that'd be 12 millimeter or smaller. We like to keep it at. Um, Certainly it's very application dependent. I see you're referencing specific pellets, and a lot of it will depend on, again, the roll diameter. With the larger roll we get, we can usually accommodate slightly larger material because we are able to better grab that material and pull it down into the rolls. So, and also it will depend on the corrugations we have. You know, if we get a coarser corrugation, we're able to pull in bigger material. However, you're not able to grind it as fine. So just kind of based on what you're saying here, the 10 millimeter really doesn't scare me overall. It's certainly something we'd be willing to look at.
Okay. Had a question that I'll tackle actually. Is the 12 by 12 machine available for purchase? Yes, it is. We've begun offering it commercially. The only model exists in our Waterloo, Iowa test center today. It is a fully modular machine. Each pair of rolls in the feeder is its own section. So it's a bit of a different design than what we have. Will, we can reach out to you individually to see if it fits your needs. Another question from Will. Do you offer a 4-inch shaft?
I don't believe so, but I may have to confirm that.
Okay.
I don't know that one
Well,
off the
we
top of my head.
reach out to you.
Yeah.
We can answer that question in greater detail for you, Will. Question, can you expand on balancing the top and bottom rolls when we only have one motor? What does that mean?
Absolutely. So I just brought the slide up again. So this is showing one of our DPRM machines where we have one drive motor driving 2 of our fast rolls. So the difficulty with that is, you're trying to make sure you're balancing the work you're doing on each set of rolls, but you can't strictly look at the amps you're running because you're grinding in both sets of rolls and those amps are being only recorded in one place. So the way to do that, there's a couple steps to it to make sure we're not over grinding or under grinding on them, would be to turn your machine on, and just with no load going through the machine, you're going to record those idle amps. And then you're going to start running and grinding as you normally do, and you're going to record your operating amps. Now, the thing to do at that point then will be to open the bottom set of rolls. That way you're not overloading them or overloading the top, because the top will still be grinding as it normally would. And then when you open those bottom set of rolls, you're gonna see your amp load drop. And so that amount of amps you drop, that change or delta, will show you how much work you're doing on the bottom pair. So then you can compare that to what your total operating amps are, and you can subtract out your idle amps, your idle amps, and the amps you lost by opening the bottom set of rolls, and that'll tell you how many amps you're pulling on the top set, and then you can also see how many you're doing on the bottom set. And so hopefully those numbers are pretty close in relation to each other, so you can see how well you're balancing them. Hopefully that answers the question. I get it is a little confusing, and if it's not, certainly feel free to reach out and we can help you figure it out as well.
Okay. Do you have small research roller mills? This was asked a couple of times. Our smallest roller mill is 6.5 inch diameter by 9 inches long. That is our smallest machine that we can handle. Do have a number of research facilities using that. Tends to work pretty well. Do the Bellevue disc springs wear out? How do we know when it's time for a change?
As with everything, yeah, they do wear out, just not very quickly at all. It would be hard to tell, I guess, because what's going to happen is they're just not going to hold their compression as well. I honestly don't have a great answer for that, other than if it's been a long time. Obviously long is relative, but that's what you would see, is that you're not able to hold your roll position as well.
Have you evaluated the impact on grinding on varying speeds of the rolls with a VFD?
The quick answer to that is yes. That's actually something we do many times in our test center. Is we do have a VFD on our main drive, so we can speed up or slow down the rolls depending on the application. So it is kind of application dependent, but yes, that's something we do sometimes look at.
All right, next question. On a double stand, should all the rolls be the same diameter? Does it matter if you put a larger set on the top or the bottom?
Preferably, yes, they are all the same diameter. I know there's some examples where you may have a 9-inch roll on the top and a 12-inch on the bottom. I would typically prefer that you have the larger diameter lower on the machine, just because you do have that improved nip angle. And typically those are going to have the finer corrugations as well. So because you have more diameter, like we talked earlier, there's more surface area. So those corrugations will last a little longer since you have the finer corrugation. So no, it's something we can certainly overcome, and it'll work. But typically, I'd prefer that we have the larger diameter roll on the bottom.
Okay. Next question. Centered around, is the presentation available? Yes, you will get an email with a download of the presentation, including the question and answer.
Yep, and if for, like Ryan mentioned earlier, it sometimes does show up in junk mail filters, but if it's been a day or so and you haven't seen it, please feel free to reach out, and I can make sure you do get a copy of the video.
How about a PDF of the presentation?
Yes, I can share one of those as well. That won't get sent out, so if it is something you would like, do feel free to reach out, and we can see who requested this one, so I'll make sure you get one for that.
Okay. With soybeans, would you see more wear in the center of the rolls than on the ends of the rolls? Or maybe just material in general?
For material in general, usually we see it more on the ends, just because actually, I take that back. It really all depends on how you're feeding the machine. And if it's coming in at a certain angle, we're going to see one side of the machine grind more than the other. It depends a little on the corrugations you have, but typically we usually see it be pretty even across the machine if you're doing a good job of feeding it.
Okay. And final question on the list that we'll address in the webinar. Well, I'll get one more popped in. So for which application do you take different roll diameters in the same roller mill?
So I know there, back in the day, a few decades ago, I know there are machines out there that many times would be grinding two different grains. Let's say, you're grinding wheat one day and corn the next day, and you only need to use a single pair machine. They would have a double pair machine, and they would only use one roll at a time. So that's a lot of the machines that are out there, like I mentioned, where there might be a 9-inch roll on the top and a 12 on the bottom. That's something where we would see that, where they were just happen to be using different commodities and just had a different requirement. We prefer to not have different roll diameters in the machine, but that's what would sometimes happen.
Yeah, I would say that's not a standard offering by our company.
Correct, but
used to be.
Yep, not a standard. What I have also sometimes looked at, we talked a little bit about being able to upgrade your rolls from either 12-inch to 1375 or 14 to 16. I have seen it where someone had a double pair 12-inch machine, and just for capital costs and budgets, they were only able to do one set of rolls at a time. So they upgraded their bottom set of rolls to 1375 and kept the top pair at 12-inch. But the plan is in the future to change that to the larger diameter to get those benefits.
Okay. Do slower roll speeds give better control of the grist of materials in animal feeds?
To a certain point, yes, because those rolls aren't going as fast. We don't have as high of a grinding action, I'll call it. We do sometimes see less fines produced, so it gives you a little more control. I think that's kind of what you're asking. Then we do certainly have to look at the case of, by slowing down the rolls, we're also not getting as much throughput as well. So that's a little bit on the backside, but yeah, there is some merit to going a slightly slower roll, we do get a little less fines produced.
All right, that is the end of our questions. You have Doug's contact information. Feel free to reach out with additional questions. There's a few that we chose not to tackle here during the webinar. We pledged to get back to you individually with some of those answers, or sorry, with those answers. And with that said, that concludes the webinar today. I want to thank everyone for attending. Really appreciate it. Thanks, Doug, for taking on this topic, and look for more topics from CPM in the future.
Thank you, everyone.
Thank you.